Well, this is it. This is the context for all of our lectures this semester on severe and hazardous weather. This thin layer of gases sitting atop our planet. We need to understand all of the incredibly turbulent motion that we get inside this layer of gases. Well, let me tell you a little bit about it. I'm going to take you back to June 11th, 2013, 2 o'clock in the morning. On that night near Grand Island, Nebraska, a decaying thunderstorm, much like the one that you probably see right here, had formed overhead. And as that thunderstorm put down its last effort at putting down a downdraft, that's a pocket of air that's descending beneath the thunderstorm full of precipitation, okay? As that downdraft descended, the air near Grand Island was so dry near the surface that all the rain evaporated. And that left this descending pocket of now dry air. Well, the atmosphere and its pressure compressed in on that pocket of air as it descended. And as it did so, it really warmed it up, compressionally warming that pocket of air. By the time that air hit the ground, that downdraft had a speed of almost 100 miles an hour, and it hit the ground and spread out horizontally on either side. And as it did so, it brought with it the heat from that compressional warming, taking a temperature sensor just outside of Grand Island, Nebraska, from a temperature of 70 degrees Fahrenheit just a few moments before the downdraft got there to over 90 degrees a few moments later. You see, that's a heat burst. And our atmosphere is full of incredible things like this, from hurricanes to tornadoes to floods to drought to extreme weather. All of it we're going to talk about this semester. And that's just a little flavor. Now, to get us to understand a bit about our atmosphere, I want you to know some of the basics about it. In other words, how big is it? How thick is it? What is it composed of? Let's start there. If you went to the surface up to the top of the atmosphere, TOA, we generally define the top of the atmosphere being around 120 kilometers above the surface. That's about 75 miles. Now, in reality, there is no top of the atmosphere because we found air molecules from Earth's atmosphere floating around 500 miles from the surface. But the point I want you to understand is this. I'm going to go up about halfway, about 36 miles above the surface of the Earth. What's interesting is that at that altitude, 99.9% of the mass of the atmosphere is still below it. Above it, you still have half the distance to get to the top, yet only 0.1% of the mass is in this layer. Now, why is this? Well, due to gravity, air density decreases rapidly with height. In fact, it is an exponential decrease in air pressure or air density with height. And that's important. Let me give you another example. I'm going to put a line right here. That line is roughly around 7.5 miles above the surface of the Earth. That's pretty high. This is a pretty high altitude for a jet. So if you've ever flown that high, 75% of the mass of the atmosphere, the air, is below you. And that's just pointing out how rapidly pressure and density decrease with height. So let's start here as we try to unpack all of the amazing things about Earth's atmosphere. Next, a couple of fun questions. You got a list of gases: hydrogen, nitrogen, oxygen, carbon dioxide, water vapor. Which of the following gases is the most abundant gas in Earth's atmosphere? Think about it for a second. Okay, hang on to your answer, because we're going to get to that answer in just a few moments. Here's another question. What do you think the approximate value of the globally averaged surface temperature is? In other words, look at the entire planet, average the air temperature across its entire surface. Do you think it's 0, 20, 40, 60, 80? What do you think? Well, let's answer these two questions because they're fundamental to understanding Earth as both an atmosphere that contains a weather and also a climate system. So let's figure this out. First, I got a list of all the gases here that are in Earth's atmosphere: water vapor, nitrogen, methane, ozone, carbon dioxide, oxygen, argon. There's actually a whole lot more, much smaller concentration trace gases. But this pie chart shows you what the composition of the atmosphere looks like when we exclude water vapor. And we'll talk about why we do that in a few minutes. Well, it turns out the most abundant gas is nitrogen. Nitrogen makes up 78% of the air in the atmosphere. Second place, oxygen. 21%. We should be glad that oxygen's not in higher concentration. If it were, fire would be much more common. In fact, a little tiny spark, if you kind of drag your feet across a carpet and touch a friend's like woolly sweater in the middle of winter, might ignite the sweater. So be happy that we don't have more oxygen than that, but also be happy we don't have less. If we had less, it'd be much harder to survive as human beings. So we have this mixture where 99% of the gases in Earth's atmosphere are nitrogen and oxygen. Well, these other gases, methane, ozone, CO2, carbon dioxide, and argon make up this little sliver. Water vapor can occupy up to about 5% of the total mass of the atmosphere. In other words, it can push these other gases out of the way and take up to about 5%, but that's only deep in the tropics. And we're going to talk more about that when we get into our lectures on water in the atmosphere. But you see, when we think about these gases, I want you to know something very simple about them. It is the mixture of these gases that keeps Earth warm. Now, check this out. This is some really cool stuff about Earth's atmosphere, okay? All of these gases, oxygen, nitrogen, all the way to the water vapor and argon, all of them are almost completely transparent to the sun's peak energy output. Now, what is the sun's peak energy? Well, it's a 6,000 degrees Celsius ball of fire. That's its temperature on the surface. It's much, much, much hotter in the interior. But on the surface, it's around 6,000 degrees Celsius. And an object that's that hot emits visible light. So that's why we can see our sun. Our eyes are designed to see visible light. Well, as that energy from the sun hits our atmosphere, none of the gases get in the way of it. Therefore, all of that energy makes it down to the surface. Now, here's what I want you to get. I've got two separate Earth, atmosphere, and sun. See that? Here's the Earth, here's the atmosphere, and here's the sun. I'm going to make this situation on the left here, this atmosphere, only be composed of oxygen and nitrogen. Make the one on the right composed of oxygen, nitrogen, and the greenhouse gases. Which of these gases listed over here except for argon? Argon is a lazy gas. It's not reactive in our atmosphere. So this is what I want you to see. These yellow arrows, they represent the peak of solar energy, visible light. In both situations, our atmosphere that's composed only of nitrogen and oxygen, or our real atmosphere, the one we actually have, which is on the right here, that light gets through to the surface. Now, when that light gets through to the surface, it hits the surface and it's absorbed, kind of like when the sunlight hits your skin and it's absorbed and you warm up. The Earth warms up in turn. Now, it's not going to get up to 6,000 degrees, but that's because we're too far away from the sun to absorb its most intense energy. But the Earth's surface is going to warm up. Now, as it warms up, this is what I want you to know. The Earth isn't going to radiate its heat back to space. It has to. It can't continue to just absorb energy all the time. If it did, it would get hotter and hotter and hotter and hotter every single day. Instead, what comes in must go back out. Now, this is what's neat. Oxygen and nitrogen, look at bullet point number 2 up here. Oxygen and nitrogen are also transparent to the Earth's peak energy output. That's thermal infrared energy. That's the energy that is released in the longer wavelength part of the electromagnetic spectrum. That's the heat that the Earth is releasing. I'll show you what that looks like later on when I show you some pretty awesome pictures and videos with a thermal infrared camera. Now, what this all means is, this red arrow, which represents this long wave thermal infrared energy leaving, in the atmosphere composed of oxygen and nitrogen only, that energy, once it gets here, well, just keeps on going to outer space. But you see, we don't have an atmosphere composed only of nitrogen and oxygen. There is this thin sliver with methane, ozone, carbon dioxide, and at even greater concentrations here, water vapor, which isn't represented in this particular graph. Those gases, these top 4 listed here, are greenhouse gases. And the key distinction is, while the oxygen and nitrogen are transparent both to the sun's energy and the Earth's energy, basically acting like a revolving door, these greenhouse gases are kind of like a one-way door. They let the sun's energy in, but as the Earth emits its long-wave radiation, the thermal infrared stuff, it's absorbed and then emitted in all directions. And because some of that energy is emitted to the left and to the right and back down toward the Earth, this retains heat in the system. You see, Earth is much, much warmer than it would be without these precious greenhouse gases. In fact, look at this. Earth's average global surface temperature without greenhouse gases, GHG, is 0 Fahrenheit. With them, Earth's temperature warms 59 degrees. Earth's average surface temperature is almost 60 degrees. And that 60 degrees of difference here is all because of these very, very low concentration gases. Now, later on this semester, at the end of the semester, we're going to have a whole lecture that tries to help us understand what is global climate and how can it change. But it's going to boil down to some pretty simple stuff, which we're going to talk about again in that lecture. Because these gases are in such small concentrations, yet has such an enormous effect on keeping Earth warm. Remember, without them, we drop about 60 degrees. In other words, Earth will be covered in ice. Well, because having these small concentration gases, we get this major benefit of being warm. It's one of the reasons why we get to live on Earth. So it should stand to reason that any changes in these gases will have a dramatic effect on Earth's temperature. And they do. It's called the anthropogenic greenhouse effect, the human-caused greenhouse effect. The natural greenhouse effect is very beneficial, but when we change it by changing the concentration of these gases, well, the planet can get warmer or colder. And right now, it's getting much warmer because we're increasing the concentration of all of these gases, believe it or not. So let's take a look at the differences between weather and climate, because a lot of times that's one of the things that's difficult to understand. What is weather? I got the definition right here. Weather is the highly variable day-to-day changes in temperature, pressure, moisture, rain, all that kind of stuff. It's normal for temperatures to be plus or minus 15 degrees Fahrenheit around the average. So check this out. I got a temperature graph here going from January 1st all the way through late summer right in through here where we see the blue lines. But the graph in the background goes throughout the entire year. You see, this is a daily temperature data map. Now, when you look at this, a few things to point out. The blue line is the daily high and low temperature in Champaign, Illinois. And you can see that it bounces all over the place. Some days we have a 20, maybe even 25 degree swing in temperatures between the high and the low. It's very normal for the temperature to go up and down, rapidly varying throughout the day. But when you take all of that year over year and average it, for example, in this particular thing, we're looking at not only record maximum temperatures, which is a line on top, and record minimum temperatures, but the normal range of temperatures, which is right here and through this color, and the average, which is the black line. You see that average is obtained by taking all of the temperature data for every given day and averaging it. What's amazing is this. In a typical year, the number of times where the daily high temperature matches the daily average high temperature, that may only happen 4 or 5 times a year. Weather is highly variable. When you average it, you get climate, and that's the smooth black line. Climate change occurs when the black line moves, not when you have the up-down movement here on the daily highs and lows. Now, just so you know, records are typically set when we're at least 4, maybe 5 standard deviations away from the mean. So that's how you get these lines that are on top. But look at this. This is highly variable weather. Let me give you another example of this. When we think about what happens when climate changes, check out this animation. What you're looking at here is a distribution of summer temperatures, and we're sliding a 10-year window from the 1950s all the way to the 2000s. You see, when the distribution shifts like it's doing here, where the mean, the median, and the mode, or the shape of the distribution itself is changing, that's an indication of climate change. You see, these are northern hemisphere summer temperatures. And what we just saw was that the average shifted toward warmer temperatures. The distribution flattened out, actually giving us more really cold events and a whole lot more really, really warm events. And therefore, this is making things more extreme. This is caused by the changes we're experiencing by impacting the greenhouse effect. And we're going to talk a whole lot more about that when we get to our climate change lectures later on this semester. Well, let me give you another example of weather, though, so you can compare and contrast. You see, weather can change dramatically. Check this out. Here we are in St. Louis, Missouri. On this day back on January 29th, 2008, a powerful cold front, you can see it right in through here, was racing out of the northwest towards St. Louis. You see, throughout the day, though, St. Louis had this strong southerly wind, bringing the temperatures there up to 70 degrees Fahrenheit. But on the backside of that cold front, well, temperatures went from 25 to 20 to 15 to 10 to 5 to 0. And in a 6-hour time period, that cold air had swept all the way through St. Louis. And on that day, they set a record high temperature right there of 73 degrees Fahrenheit. And by that night, the temperatures had dropped all the way down to here, all the way to 15 degrees Fahrenheit. It's a 58-degree drop in temperature in one day. You see, that happens. Day-to-day variations can be huge. But it's when we see shifts in the averages that we're experiencing climate change. So I want to get that out of the way first so that when we talk about climate change later on this semester, you've got a good benchmark for it. So let's keep going here. I want to talk about the human thermometer. You know, a few years ago, I had a class that was all about instrumentation. We were teaching students about weather instruments. So one day when I was about to teach them about thermometry, I had them all come in as a nice end of summer day at the beginning of the school year, and I asked them to all write down what they thought the temperature was outside. Now, the temperature outside was 84 degrees. I had some students who thought it was 98. I had other students that thought it was in the lower 70s. In fact, there was a huge distribution around the mean, which basically means humans are horrible thermometers. Let me give you another example. Imagine you were watching this video and it was the middle of winter. You know, if there was a hot tub and the temperature of the water in the hot tub was 105 degrees, boy, you'd want to go sit in that, right? It would feel amazing. Yet, if I took the air temperature in the room that you're watching this video in right now up to 105 degrees, it would be absolutely stifling and disgusting. Same temperatures, different ways by which we perceive it. Or imagine this, in the middle of that cold winter day, if the temperature outside warmed up to 60 degrees, oh, we'd all go outside and enjoy it. But if I were to throw you into a lake where the temperature was 60 degrees, you might become hypothermic in as little as 30 minutes. You see, the human body, while it is very sensitive to changes in temperature, is horrible at measuring the absolute value of it. For example, this slide you've been looking at here, it says the 300 Club. Well, it turns out there's a club you can join if you go down to the South Pole. And down there, on the first day when the temperatures get out to minus 100 Fahrenheit, there's a sauna that people will sit in where they keep the temperature up to 200 Fahrenheit. And the goal is, when you get up to 200 degrees Fahrenheit inside the sauna, strip off all your clothes and run outside. And do this so that your body can experience a 300-degree swing in temperature. Now, all you get's a little patch for it and some bragging rights, but I imagine that would be a pretty amazing sensation across the body. Let's talk about the definition of temperature. Here it is. The definition of temperature is this. It's a measure of the average speed of all the molecules in a substance, like a solid or a liquid or a gas. Now, that's an interesting definition because it's one of those things where if you ask someone to define temperature, they might define it by giving you, adjectives like it's hot or it's cold. But really what it is it's the average kinetic energy of the molecules in any substance. So all molecules at all times are moving, even in solids. They're vibrating in place. And that's because if they stopped vibrating, well, technically they cease to exist. We call that absolute zero, but we'll save that for a physics lecture. We can see, the molecular movement on a much bigger scale here when we look at boiling water. Now, when you look at boiling water, what you're actually seeing are these pockets of water vapor that are coming up off of these hot spots at the bottom of the pan, but you can see the turbulent motion in the liquid here. So we can get an idea that the molecules are moving much, much, much faster as they're more energetic and higher temperature. Here's a piece of iron that's been heated so much that its molecules are vibrating so violently that they're glowing. They're actually releasing photons of light. We can see these two things pretty clearly with our eyes, but we can't see gases. Our eyes cannot see gases. It's impossible. But I can at least represent them for you like this. You see each one of the blue dots in here, let's let that be a nitrogen molecule, and the red one's an oxygen. You see here in a container full of gases, the molecular motion of the molecules, the gases in there, to cause the air to kind of vibrate and move. Now this is not wind. This is just the molecular motion of air. So average speed, average kinetic energy of the molecules in a substance. That's the definition of temperature. Now here's a fun question. There are something like 206 countries around the world. How many of them do you think use the Fahrenheit scale as their primary temperature scale? Look at what I got here. 5, 45, 90, 115, 145. Take a quick guess. Okay, got your guess? Here's the answer. 5. The US, the Cayman Islands, Belize, Liberia, and Myanmar, also called Burma. That is it. That is the only countries I could find that actually use the Fahrenheit scale. So if you are watching this in the United States, let me tell you something. You got to get used to start using the Celsius scale. That's a scale that's more widely used around the world. Now, when we look at these two scales, I got them both over here on the right-hand side. There's a couple of things I want you to know about them. First, the Fahrenheit scale. If you want to convert over to Celsius, here's the equation. Okay, so it's right down here at the bottom. But more importantly, I want you to know about the discovery of both of these scales. Daniel Fahrenheit, a scientist, came up with his original scale. He wanted it to be something like 100 degrees was a really, really hot day and 0 degrees was a really, really cold day. But scientifically, he broke his scale up into what you see here. Now, Celsius, another inventor came along, another scientist came along and made up a little bit different scale. This is the one that's used in that's more commonly used in science, or Kelvin, which is just an offset of Celsius. Now, some numbers I want you to know on these scales. 134. You see, on this device called the thermometer, 134 turns out to be the record high temperature we've ever measured on Earth. Now, I want you to know something. That's an air temperature. And to be an official temperature measurement, it has to be made at 2 meters. That's 6 feet above the ground. So, of course, the air's been much, much, much hotter than that right next to the ground. I mean, in the middle of summer, go out to an asphalt parking lot, you can measure temperature right there above the ground. It may be much, much, much higher than 134. But at 2 meters or 6 feet, 134 is the record. Now, what's interesting is this record was broken in 2012. You see, here in the desert in Libya, in 1922, a record was set of 136 degrees Fahrenheit. That's about 57 degrees Celsius. And that record stood until 2012. You see, in 2012, it wasn't as though the record was broken in the way that traditionally records are broken, by setting a new high. It turns out that a bunch of meteorologists and scientists and data analysts got a hold of the data from that particular thermometer, compared it to some nearby thermometers, and discovered that about 2 weeks before the record high temperature was set in Libya in 1922, that the thermometer broke and developed a 7-degree bias. And once that was discovered, that record was thrown out, and it was reestablished back in 1913 in Death Valley, which is in Southern California. And that number stands at 134 Fahrenheit. That is the hottest it's ever been at 2 meters that we know of, that we've measured here on the surface of the Earth. What about 98.6? You probably know that number as the average body temperature. Turns out, though, that Daniel Fahrenheit, the guy that gave us the Fahrenheit scale, found that temperature by sticking his very rudimentary, very large thermometer into his wife's armpit and left it there for 2 hours while it reached equilibrium, and discovered that her body temperature was 98.6. What about 59? Well, remember that number. That is Earth's average temperature in degrees Fahrenheit. That's 15 in Celsius. 32. This is probably a number a lot of you know. At 32 degrees, we're commonly taught that at 32 degrees Fahrenheit or 0 Celsius, water will freeze. You're going to learn pretty soon that that is not always the case. What about minus 40? This is kind of a fun number to know. At minus 40 degrees Fahrenheit, that is the only time where the temperature scales for both Fahrenheit and Celsius are the same. So minus 40 Fahrenheit is also minus 40 Celsius. And finally, the record cold temperature, which is in Vostok, which is in Antarctica, was set at minus 129. And at those temperatures, alcohol will freeze. So these are just some fun numbers to know and understand about temperature. Okay. What I want to do with this information is I want to start talking about why understanding temperature is crucial to figuring out meteorology, especially high impact and severe meteorology. Now, check out this video. We're going to watch a hot air balloon race in Reno. Now, it's time-lapse. We're filling canvas with hot air. And as the hot air fills the canvas, it becomes buoyant and it rises. I mean, look. This is very heavy. There's heavy canvas. There's a heavy basket at the bottom. They're carrying people and propane and sandbags and all sorts of stuff like that. Yet somehow it's able to become buoyant and float in the atmosphere. If you understand how this works, you will understand the very, very basics of how the atmosphere can produce some of its most amazing and severe weather. So let's figure this out. All right. The thermometer, how does it work? Well, at the bottom of a thermometer, we keep a fluid, typically alcohol or mercury. But it's in a sealed system that's been evacuated of air. Now, because when you heat up a substance, you force the molecules to vibrate faster, well, the faster they vibrate, the more room they need to move around in. And the more room they need to move around, well, they're going to seek that room out. And in this case, as we heat up a thermometer, they seek out room in the little tiny kind of cylinder that runs right up in the middle of this thermometer, and the temperature rises. Because it's so small and so controlled, we can actually tick off on the side here and tell us exactly how warm the temperature is. So here's the idea. The higher the air temperature, the faster the molecules move. We learned this a few moments ago. We also just learned that the faster the molecules move, the more space they need to move around in. Basically, increasing the temperature of a substance, like air, causes it to expand. And that's what we want to write down here. You see, warming the air causes it to expand. Cooling the air causes it to contract. So why the hot air balloon can float? We've heated the air on the inside with a giant fire. Okay, there's basically burning propane, forcing it into the inside of this canvas. Heating up that air causes it to expand. That lowers the density, and that makes it buoyant, allowing it to rise through the cooler air on the outside into the atmosphere. This is also why when we say, warm air rises, that's because warm air is less dense than cold air, and therefore warm air rises. Let me give you an example here. I took this picture. This is in Champaign, Illinois. Got this high-rise apartment complex on Springfield Avenue. Now, the question is, where do you live if you have to live in a high-rise apartment? Do you live in the top, do you live in the middle, or do you live on the bottom? Well, when I think about this, I think about students that come to the University of Illinois. We're typically here at the end of summer, all of fall, most of winter, all of winter, and then the beginning of spring. So we're here during the cooler time of the year. Now, if elevator traffic isn't an issue for you, I would tell you to live near the top. Why? Well, the warm air from the apartments below you will basically rise. It's less dense, therefore keeping you at the top of the apartment complex warm during the cold season, therefore lowering your bills. Now, if you live here during the summer, don't live up there. Live near the bottom. It's much, much cooler near the bottom. So this is just a practical example of what we just discussed. Let me give you another example here. Have you ever seen these, on the side of a fan, like a ceiling fan in your house or apartment, that there's a little switch that's labeled reverse? You see, it's important during winter to use your fans. And that's because in winter, if you reverse the direction, they'll actually blow air up toward the ceiling rather than down onto your skin. Now, what's the benefit of this? Well, not only does it push some of that heat that's up here near the ceiling back down, but it'll actually push the air that's really warm up near your ceiling over toward the walls. And as it hits the walls, it more evenly heats the room, and therefore it lowers your energy costs. Now, during summer, you want to actually have the fan blow down. And that's because you want to get this cooling effect as the air rushes across your skin. So run your fans all year long. They use a very, very small amount of energy, and they can actually keep your bills lower by keeping you cooler in the summer and warmer in the winter. So just an example of how heat rises. Let me give you another example. This is a picture of an expansion joint in a bridge. Now, why I'm showing you this is because if you ever build solid state structures, like a bridge, you build out of concrete and metal, asphalt, and those kind of things. Well, when those materials heat up and cool off, they expand and contract. If you don't build a mechanism in, like this expansion joint, to allow the bridge to kind of expand and contract, it'll crumble. So whenever we build large structures, we anticipate the expansion and contraction as changing the size of a building or a bridge or anything like that. So it's very, very important that we pay attention to these very simple ideas here. So as we continue on with our lectures, keep these ideas in the back of your mind. They're going to be central to everything we're going to be talking about as we dig through all of our different severe weather topics.